Good morning everyone. We are the group that will explain our final project under Net313. Project title is Advanced Network Architecture with DHCP and AIGRP Optimization. For the project task, Part 1, Company and Network Requirements. Our company name is EduConnect Systems. EduConnect System is an educational institution that serves a wide range of users, including students, teachers, administrative staff, and campus visitors. It operates across 3 locations, its headquarters, the San Fernando branch, and the Bacolor branch. The institution provides essential digital services such as online learning platforms for virtual classes, administrative systems for managing student records and enrollment, research tools for accessing digital libraries and academic resources, and internal communication tools that support collaboration among all users. Because it supports many functions and locations, EduConnect system relies on reliable and secure network connectivity to ensure smooth delivery of its educational and administrative services. For the business networking requirements, for EduConnect system focus on ensuring smooth and efficient communication across all locations. Reliable inter-branch connectivity is essential to maintain seamless communication between the headquarters and its branch campuses, supported by properly configured WAN connections. Each site also needs stable local connectivity through a well-designed LAN to enable internal resource sharing among PCs, servers, and other devices. To keep the network organized and efficient, centralized address distribution using DHCP is implemented to automatically assign IP addresses. For flexible and robust routing across the entire network, AIGRP is applied as the dynamic routing protocol. The network scalability is supported through subnetting, allowing room for future devices expansion in every location. Finally, regular testing and failover simulations are conducted to ensure network reliability, performance, and readiness for unexpected link failures. For the Part 2, Network Design and Planning, this network diagram shows the complete setup of the EduConnect system network, including the headquarters and its 2 branch campuses. The design illustrates how all locations are interconnected to support communication, resource sharing, and administrative operations. At the center is the headquarters, which acts as the main hub of the network. It contains multiple devices, including PCs, laptops, and a server, all connected to a central 2960 24TT HQ switch. This switch distributes connectivity to the internal devices and connects them to the HQ 2911 router. The HQ router is responsible for linking headquarters to both branch locations and through WAN connections. Next is the physical view of intercity and city. The intercity physical view shows how the main locations of EduConnect systems, such as the headquarters, San Fernando branch, and Bacolor branch, are geographically separated across different areas or cities. This view highlights the wide area connections that link these locations together. On the other hand, the CC physical view focuses on the layout within a single city or community. It shows how several network sites or buildings inside one area are connected through local cabling. This slide displays the physical layout of the network devices in each EduConnect system location: the headquarters, the San Fernando branch, and the Bacolor branch. Each image shows how the routers, switches, PCs, and laptops are physically arranged and connected inside their respective network racks and workstations. Next is the explanation of our design and decisions. The network was designed with the headquarters serving as the central hub where all communication between branch offices is routed through the ECS HQ router to simplify management, monitoring, and security control. Serial WAN links were used to provide reliable point-to-point connections between HQ and the branches, ensuring stable intercity communication. To streamline IP address distribution, the HCP was centralized at the HQ router, with branch routers using the HCP relay to forward client requests, allowing easier administration and consistent addressing. For routing, AIGRP was selected because of its dynamic, efficient, and scalable features, making it well suited for medium-sized networks like EduConnect system. Finally, subnetting was applied to organize and scale the network, assigning different subnet sizes to each location: 192.168.5.0/24 for HQ, 192.168.10.0/24 for San Fernando, and 192.168.15.0/24 for Bacolor, ensuring each site has enough address space for current and future devices. For configuration and implementation, the network Configuration began by setting up the complete topology for all EduConnect system locations. At the headquarters, one router and one switch were deployed, along with 3 PCs, one laptop, and a dedicated server. The San Fernando branch was equipped with one router, one switch, 2 PCs, and one laptop, while the Bacolor branch included one router, one switch, one PC, and 2 laptops. All devices within each location were connected using copper straight-through cables, linking the router to the switch and the switch to all PCs, laptops, and the server to form each site's LAN. For inter-branch connectivity, serial 1 links were used. The ECSHQ routers serial 0/3/0 interface was connected to the San Fernando router, and serial 0/3/1 was connected to the Bacolor router. This setup established both the local and wide area network connections necessary for seamless communication between all EduConnect system locations.
Hello, my name is Rain Rivera, and this is my part. Configure the devices. A. Configure ECSHQ router. Set hostname and basic configuration. First, access the router and enter global configuration mode. Type enable, then configure terminal, then hostname ECSHQ router. Then next, configure Gigabyte Internet interface. Configure the LAN interface with its IP address and activate it. Type type interface Gigabyte Internet 0/0. Enter then IP address 192.168.5.1, 255.255.255.0. Now shut down, then exit. Now set up the one connection for serial 0/3/0 and serial 0/3/0. As you can see here, type type the following. Then B. Configure the SF router. Set host name and basic configuration. Enable configure terminal host name SF router. Next, configure Gigabyte Ethernet interface. Type interface Gigabyte Internet 0/0. IP address 192.168.10.1. 255.255.255.0. Now shut down. Then next, exit. Configure serial interface. Interface serial 0/3/0. IP address 10.0.0.2. 255.255.255.252. Now shut down, then exit. Next is configure VR router. Set host name and basic configuration. Enable, enable, then configure terminal, then host name VR router. Configure the Gigabyte Internet interface. Type interface Gigabit Ethernet 0/0. IP address 192.168.15.1. 255.255.255.0. Now shut down, then exit. Configure the serial interface. Type interface 0/0/3/0. Then the IP address is 10.0.0.6. 255.255.255.252. Now shut down, then exit. Configure the switches. Set hosting and VLAN IP for each switch. For EduConnect System HQ switch, just type this, enable configure terminal, hostname, ECS HQ switch, interface V1 LAN, IP address 192.168.57, 255.255.255, shutdown, then exit. For San Fernando switch, as you can see here, just type here, you can see the San Fernando switch. And as for Bacolor, just type here like here, then next, configure the DHCP on ECSHQ router. Set up the DC, DHCP pools for ECH, SHQ, San Fernando and Bacolor branches, like right here. Pipe IPD DHCP pool ECSHQ network 192.168.5.0 default router 192.168.5.1 the DNS server 8.8.8.8 that exists next IP ECHP as a router network 192.168.10.0 255.255.255.0 default router 192.168.10.0 DNS server 8.8.8.8 the next one IP IPDHCP full BR router network 192.168.15.0 255.255.255.0 default router 192.168.15.1 DNS server 8.8.8.8 the next it configure the D the DHCP relay on branch router. Here is for SF router interface gigabit Ethernet 0/0 in IP hyper address 192.168.1 then exit for BR router interface gigabit Ethernet 0/0 IP hyper address 192.168.0.1 then exit. Next is configure PC for for each PC, go to desktop tab, then IP configuration, set up configuration to DHCP is an example of this. Then configure the EIGRP for routing, enable EIGRP on all routers. Then type what's in here, the router EIGRP 100. Then for verifying EIGRP configuration, for checking neighbors, show IP EIGRP neighbors. Next is for checking the router table, show IP route. Next, for passwords, I do I do connect system HQ router, set enable password for privilege mode, enable secret EC is HQ. Then set console password for physical access. Line 10 password ECSHQ 123 login then exit. For BTY password for remote access via telnet/SSH. Line VTY04 password ECSHQ456 login then exit. Then for San Fernando branch router, set enable password for privilege mode, enables secret transfer, then set console password for physical access, 9con0, password transfer 123, login then exit. For VTY password for remote access, 9VTY404, password transfer 456, login then exit. Then for Bacolor branch, set password for privilege mode, enable secret Bacolor. Then set console password for physical access, line con 0, password Bacolor 123, login, then exit. For VTY password for remote access, line VTY04, password Bacolor 456, login, then exit. For testing and verification, ping across the network, testing connectivity between PCs at different locations, like ECSHQ PC1 to Bacolor PC1. Validate DHCP, check DHCP IP allocation using show IP DHCP findings for testing EIGR-free failover, simulate a link failure by shutdown one serial interface, type configure terminal interface serial 0/3/0, shutdown the next hit. Observe route adjustment using show IP EIGRP topology. And that's it. And that's it for my part. Thank you.
Next, Part 4, Advanced Testing and Analysis. My section focuses on how the network behaves during failures and how routing protocols respond to those changes. First, we simulate and test the network under both and failure conditions. In normal operation, we verify that all branches can communicate with headquarters. Then we intentionally shut down devices or link to see whether the network can handle interruptions and whether dynamic routing protocols react correctly. Uh, in this part, we simulate devices by temporarily disabling routers or interfaces. While the failures is active, we watch the routing protocol updates and how the remaining routers recalculate new paths so that the traffic can be reach its destination. Here we simulate a failure in a San Fernando branch here, and after shutting down the device, we run the command show IP route to check the routing table if OSPF are OSPF and EIGRP are working properly. The route to San Fernando is removed or marked unreachable, which shows the network has reconverged. In this routing table, we see the C for connected, L for local, and D for ER, EIGRP, and O for OSPF. When the San Fernando route disappears from this list, it confirms the router correctly detected the failures and update its routing path. Next, Bacolor branch. We repeat the same process for Bacolor branch. After shutting down the device or link, we run show IP route if Bacolor network disappears or changes. Here we can see Bacolor neighbor is no longer listed. At the same thing with San Fernando, neighbor is no longer listed. And after we confirm the routing protocol, recalculate and remove unreachable routes. These tests help us to verify the correct dynamic routing behavior. The protocol should be remove fade routes, select a best uh, new best path quickly, and avoid sending traffic to offline branches to keep the network stable. Next, we restore the San Fernando and Bacolor routes. Once we back online here, once we back online, we can check connectivity and confirm the both branches successfully reconnect to edge quarter router. Running show IP route again, we now see all expected network. This confirms that the network recognized active links and the topology as returned to normal. Then, we can check EIGRP neighbors relationship. During the failure, the San Fernando and Bacolor entries disappear from the neighbor table, which is expected when the routers go offline. Using the command show IP EIGRP neighbors, we verify the adjacency is lost during shutdown and re-established after restoration. This demonstrate the EIGRP's ability to quickly adapt to topology changes and prevent traffic from being sent to unreachable devices. Uh, in summary, network the network correctly detects failures, update routes, and restores connectivity once devices come back offline. With this behavior, with these behaviors confirmed, we can proceed to the next section where we analyze protocols response times and overall network stability during failures.
Simulation link failures were applied to both San Fernando and Bacolor branches. After disconnecting the San Fernando link, the routing table was examined using the show IP route command, and the results confirmed that all routes leading to San Fernando were removed, indicating that the branch was no longer reachable in the network. A similar procedure was performed for the Bacolor branches. After simulating the link failure, the show IP route output verified that the backcolor was no longer visible in the routing table. In both scenarios, the routing tables confirmed that the affected regions were successfully isolated from the network as a result of the simulated link failures. After simulating the removal of traffic for both the San Fernando and Bacolor branches, the EIGRP topology was checked using the show IP EIGRP topology command. The results showed that all routes remained in the passive state, indicating the routers successfully recalculated their paths and the network fully converged. This confirms that EIGRP responded correctly to the link failures, removing the affected routes from topology and maintaining stable network operation. After the disconnected link was reconnected, the network was tested to verify whether the original routes were restored using the show IP route command. The routing tables displayed all previously available routes, confirming that full connectivity had returned. The show IP EIGRP neighbors command was also checked, and the results showed that all EIGRP neighbor relationships were established and stable. This indicates that the routing protocol successfully converged and the network resumed normal operation. Overall, the reconnection process was validated and the network fully recovered its original routing paths and EIGRP adjacencies.
In this photo shows the command IP config, all show the IP subnet mask gateway and DNS. Successfully received an IP address from DHCP server San Fernando PC3. Also received the correct DHP information. The presence of DHP server and list obtained confirms DHP is working. As you can see, guys, this means both computers are properly connected to the network and receiving settings automatically. In this slide, show that the PC has an IPv4 address of 192.168.15.3 and is using a subnet mask of 255.255.255.0. This indicates the PC is configured on a local network which its default gateway and DHCP server both set to 192.168.15 and 1. In this slide shows the IP configure release command tells the client device to immediately relinquish its current IP address and network settings, sending a DHCP release message back to the DHCP server and resetting the client configuration to 0000. This action makes the old IP addresses available in DHCP pool for assignment to another device. As confirmed by output in the image where all addresses are clear, network administration typically follow this up with IP config renew command to force the device immediately request a new IP address from the DHP server, which is a common troubleshooting step for network connectivity issue. In this slide, ipconfig or release command prompts the client device to instantly surrender its DHCP assigned IP address and related network parameters. This process transmits a DHCP release message to the server clearing the device configuration to 0000 and temporarily halting its network communication. Network troubleshooting often begins with this command.
IP adjacency. In the San Fernando route, we run the same command, show IP EIGRP neighbors. We confirm that it recognizes ECSHQ as an EIGRP neighbor with stable uptime and consistent timers. And in the backdoor router, the EIGRP neighbor table confirms one active adjacency with ECSHQ on interface serial 031. This validates full EIGRP convergence among the connected routers. Now we move on this slide. Analyze network performance under different traffic loads. In this stage, we focus on analyzing network performance under different traffic loads. To demonstrate this, we simulate high traffic using ping commands and observe how devices respond. Here in the screenshot, we are sending pings to different IP addresses from PC0. When we ping 192.168.10.1 and 192.168.5.1, all packets timeout. This indicates high traffic congestion or an unreachable device, resulting in 100% packet loss. However, when we ping 192.168.10.4, we finally receive replies with a very low latency, around 1 to 10 million seconds. This confirms that the device is reachable and that network communication is successful on that path. By comparing timeouts and successful replies, we can identify which parts of the network are overloaded or misconfigured. This helps us evaluate network stability during heavy traffic conditions and ensure we can troubleshoot performance issues effectively. Starting the links between Magallanes and Santolan. Once the links to Magallanes and Santolan are restored, EIGRP quickly reestablishes adjacency. In the routing table, all previously removed networks reappear, showing that EIGRP has successfully reconverged. To further validate this, we examine the topology table using show IP EIGRP topology. This output confirms that EIGRP recognizes all networks as passive with a valid feasible distance and successor routes. The routes via serial interfaces reflect that the network is fully converged again. In this slide, we're gonna test the EIGRP failover. Confirm if Magallanes is not connected. To test EIGRP's failover capability, we simulate a link failure by disconnecting the Magallanes link. After disconnecting, we verify this by checking the topology view. Magallanes shows no longer as reachable. On ECSHQ, we run show IP route EIGRP. The route to the Magallanes network is removed from the table, proving that the router has recognized the disconnection. And in confirm if Santolan is not connected, we simulate a failure of the Santolan connection. Again, in the topology, the link visibly drops. On ECSHQ, running the same routing command confirms that the Santolan route is no longer present. This demonstrates EIGRP's automatic removal of unreachable networks.
Next, we move to the packet tracer simulation mode to observe how packets travel through the network in more controlled step by step manner. On this slide, you can see multiple views on our full topology, including the headquarters and the branch network connected. via routers and switches. In simulation mode, we can generate packets such as ping or application, traffic, and they play, pause, or step through the events. Each frame in the timeline show when a packet is created, forward or queue, or drop by specific device. This give a clear visual representation of how routing updates, link states, and device configuration affect end-to-end communication. Using this using this simulation, we verify that routing protocols forward traffic along the intended paths, that redundancy behaves correctly when links or devices fail, and the packet still reach destination once the network converge. Uh, Overall, simulation mode allows us to closely analyze protocol behavior, timing, and path selection, which support our advanced testing analysis for part 4 of the project. Next, on this slide, we focus on testing network latency using the traceroute tool. Traceroute tool allows us to see the path that packets take from the source device to the destination IP address and to measure the delay at each hop along the way. In the screenshot, you can see the command prompt window from the laptop in our topology. Running the traceroute command towards the target IP address. Each line represents a hop through the network showing the gateway address and the round trip time value in milliseconds. Several entries show request timeout, which indicate that some intermediate devices are either configured not to respond to trace route or dropping these probe packets, but the trace still completes successfully at the destination. By analyzing this hub by hub, we can identify the latency is introduced and confirm the packets are following the expected path through the network. And this helps validate both connectivity and performance and provides a baseline from comparing normal operation against future failure or congestion scenarios.